Hello, Physics 2. Welcome back. This is part 1 of week 15's Wednesday's lecture. And so we're continuing on with chapter 22. So we last talked about inductance. I'm just going to rewrite this here. Mu naught n squared over d pi r squared. And so we related EMF from inductance to L di dt. So we're going to see this again, so I want to go ahead and just draw your attention to this. So, and the unit for L is something called a Henry. And we use a capital H. All right, so transformers. This is an application of what we've learned so far. So the efficient use of electrical energy has revolutionized our society. I mean, after all, I'm recording a lecture right now because of the beauty of electricity and the efficientness of using it. So it is true we've had batteries for it looks like more than 2,000 years, but really the harnessing of electricity is a relatively recent thing in terms of the history of the human race. So commercial energy if you don't know, is usually transported with a delta V, that is a V, not a U, with a delta V of orders of hundreds of thousands of volts. You do not have this much voltage in your house. So power lines typically have this much voltage running through them. So my husband, when we lived in Kansas, briefly worked as a tree trimmer specializing in cutting branches around electrical lines. So this is why you need specialized people who can do this, because what they do is actually very, very dangerous. We don't want that type of danger in our houses. And also, it's just an utterly inefficient use. We just don't need that type of voltage. So, way more than needed for home use, but good for transportation, just like we have very large water pipes that transport water, and then we get to our homes and the pipes get a lot smaller. But we need to have a way to step this down. Use. So we need to step it down. That is where transformers come in. So let's look at how this is done. All right, so let's say we have a solenoid of 1,000 turns around a cylinder of 1 meter. And then around this, we have another coil, and I'll draw a picture. Just a second, with n equals 120 turns. Okay, so this is what we've got. Here's our original solenoid, N equals 1,000. And then here is the other coil, N equals 120. And then our D is equal to 1 meter. All right, so we connect the N equals 1,000 solenoid to an AC supply. And what an AC supply is simply alternating current. So the current in your house is alternating current. When we build our circuits, we are building direct current supplies. And the main reason why we don't work with too much AC current is it's actually more dangerous. But very practical for home applications. All right, so, and this alternating current has a delta V max cosine omega t. All right, we're going to go after, we want the EMF of the second coil. So we know B1, so that's coil 1, is equal to mu naught Ni times, or N1 times I, the current D. And if the cross-sectional area of one coil is A, the EMF of one turn of coil 2 is A dB dt. And the total EMF of 2 is (120) A mu naught N1 over D di dt, which you should see. All right, so all we're doing is we're just starting to bring everything together in terms of inductance, in terms of Faraday's law, in terms of what we know of solenoids. All right, so let's compare the EMFs. So the EMF of 2 is equal to N2A mu naught N1D di dt. And EMF mu naught N1 squared D di dt. Therefore, EMF 2 is equal to the ratio N2 of over N1 times EMF 1, or 120 over 1,000, which is 0.12, times EMF 1. And if delta V max is 100 volts, then it will be 12 volts on the second coil. And that is how they step down voltage going into your house. By the way, for those of you who have gone to or lived in another country that runs on a different voltage, so Spain and the US run on different voltages, and so if you had an American appliance, of which we had a few of growing up, you'd have to plug it into a home transformer, which would adjust the voltage to the appropriate amount so you could plug it in. By the way, Nothing smells worse than a transformer blowing up, and if you have ever smelled that odor, you know exactly what I'm talking about. It is foul. So this is how a step-down transformer works. So nowadays, when I was growing up, these were actually quite large, but nowadays they build them into little wall plugs, and a lot of devices like your phones, like your hair dryers are made to run on different voltages. So, but that was not true in the 90s, which is when I lived in Spain. And I'm guessing some of you were not born yet. Awesome. Okay, so energy density. So if you recall, energy density, we've talked about it a few times, and I was asked if it would come up again, and yes, it comes up all the time. In terms of a capacitor, so you have electric energy divided by volume equals 1/2 epsilon naught E squared. So we have seen this before. We've done a little bit with it, but not much. Now, so that's energy density associated with an electric field. We can also have energy density associated with magnetic fields. All right, so let's do it. The power going into an inductor, that's our solenoid, is I delta V. So power is equal to I delta V is equal to I times EMF is equal to I times L di dt. Just plugging and chugging different definitions right now. By the way, never a bad technique when you're just kind of struggling for how to solve a problem. So also very good for doing theoretical research. Actually my theory paper came about because I did exactly this. So integrating over time, not this equation, but just sort of like, I'm gonna play with equations and see what I get. And sometimes you get something that other people have overlooked. Integrating over time, we have energy input equals I dV, or I delta V dt. So this is equal to inductance from whatever time interval we're integrating over, I di dt dt, which is equal to L I initial, I final, I di, which is equal to L times 1/2. No, general class, I do not expect you to know how to do this, but I do expect you to accept the result, which is equal to delta 1/2 to I squared. Okay, so B is equal to mu naught Ni d, and L is equal to mu naught N squared d pi r squared. And so magnetic energy equals 1/2 mu naught n squared d pi r squared times BD over mu naught n squared is equal to 1/2 1 over mu naught pi r squared d b squared. And so if we look at electric and magnetic energy densities, so this is just magnetic energy. We have not done a density yet. And just like the game we played with electric energy, we have taken advantage of our understanding of inductors to derive magnetic energy. What we have derived is actually general. If you want to work through more rigorous derivations of this, take an electromagnetism class. You will do it. And it's actually kind of fun. So energy divided by volume is equal to 1/2 epsilon naught E squared plus, remember they play together, 1 over mu naught B squared. And it is measured in joules per meters cubed. This is a general result. And actually, this is a very important equation. And you will see it. You do a lot of fun stuff, actually, with this equation in electromagnetism. See it a little bit in optics, but it's all kinds of cool. All right, and we'll get to play with it some more in chapter 23. All right, so now we're going to move on. Let me just use new paper. And we're going to move on to inductor circuits. Yes, this is one of the green sections, but it's actually important, so we're going to do it. All right, so we're going to start with current in an RL circuit. So, an RL circuit. This is an RL circuit. It has a resistor, and it has an inductor, and we've got some current I running through it. So basically any circuit with a resistor and an inductor. Then you have an RL circuit. All right, so, and they are very interesting in their behaviors, and while we won't get into it very much, there are useful applications for them. Okay, so the loop rule for such a circuit is written delta V battery, or EMF, plus delta V resistor, plus delta V inductor is equal to 0. Thank you, energy conservation. So EMF battery minus RI minus L di dt, which we just saw, is equal to 0. So just to note, the minus sign for the inductor is because the EMF of the inductor opposes current increases. So remember, I said inductors are sluggish. We're going to really take a nice deep dive look at that type of behavior by looking at different circuits with inductors in them. So it's going to fight the current until it can't. All right, so the equation setup that we see right here is very similar to that we've seen of an RC circuit. So similar equation. And some of the thinking works. It's a little bit different though to RC circuit, but that's something to kind of keep in the back of your mind. And maybe we'll put them together, eh? Could be foreshadowing. What do you think? Oh, come on, you know me too well. Of course I'm foreshadowing. So, if the circuit is connected at t equals 0, so we connect it and then we start the timer right when we connect it. I is initially 0 at t equals 0. And remember, I said that inductor wants to fight the current. Therefore, it will take time for I to stop being 0. It's not instantaneous like when you connect other circuits. Remember chapter 18, it basically just flows as the inductor will make it sluggish, but you can wear them down. So, the time-current relationship for one of these is I is equal to EMF, battery, divided by R times 1 minus e to the minus r over L times time. And 211, you should prove this. It'll be fun. All right, so it's just a derivative. So after a long t, if we look at this, we can see that eventually e to the minus r L t is going to go to 0, and then you essentially have I is equal to EMF of the battery divided by R. Oh my goodness, we've seen that so many times before. And when this happens, you have a steady state current. And now we can just play our little games like we normally do. Well, kind of. Okay, so if we look at this graphically, so we'll put I here, and then what's going to happen is you're going to have a real kind of slow and exponential start and kind of going to there. So I final equals EMF battery over R. And then right around here-ish, you have L R, which is the time constant. So, and we'll show you why LR is the time constant. I'll give you a giant hint. It looks a lot like an RC circuit. So L over R is the inductor. E to the minus R over T times T. And so when T is equal to, oops, that is supposed to be an L. So when T is equal to L over R, then you have E to the minus R over L times L over R is equal to E to the minus 1 is equal to 1 over E is equal to 0.37. You do sometimes see this written as tau is equal to L over R. So this side. And in this case, so just like RC circuits have time constants for charging and discharging, so do inductance circuits have time constants relating to reaching a steady state. So the end result of one of these particular setups is the steady state current. It's not a charge or discharge, which of course the charge and discharge is related to equilibrium. And remember, equilibrium and steady state are two different things. Okay, so so as you might imagine, these types of circuits take longer to get going. Than a typical circuit. I have found some inductors in the closet, but I have not checked them out yet. And the reason why I'd want to test them carefully has to do with the following cool fact. So, if you open, so in other words, you disconnect an LR circuit after a steady state, has been obtained, so I goes to 0 in a small delta t. This has some implications when you have an inductor, because remember, when you have a change in current, with respect to time, you have a change in magnetic field, which is definitely related to something called EMF. So we need to think about, consider the EMF in the solenoid. So you have a large delta I, delta t. Large change, very short, very short time interval. So EMF is proportional to dB dt, which is proportional to di dt. So all of a sudden you just ramp up your EMF, which can result in a spark. And a spark jumping an opening switch. I don't know if any of you have ever been shocked before. Ouchie mama, that hurts. I used to work in a dark matter lab where we built acoustic transducers, and I was busily working one evening on testing out different methods of soldering some piezos, and you know, we were handling them, and the next thing I know, I let out a scream of bloody murder because I got shocked by one of the piezos. And Austin, my friend that I was doing research with and working together with, was like, "Oh, Emily, it can't hurt that bad." I was like, "All right, fine, you try it. You see what happens." And so he started doing it, And sure enough, within 3 minutes, let out a scream of bloody murder, and we both decided that the technique that we were trialing was not a good one. And we revised the following day. Okay, so let's do an example. By the way, as there is no homework out of this section, I would recommend paying attention to the examples. You place a 60-volt battery in series in an inductor circuit with a 50 times 10 to the minus 3 Henry inductor. By the way, if you're curious, one Henry is equal to a volt second per amp. And a resistance of 180 ohms. What is the current I and the rate of change of current di dt at t equals 0? Not the same thing. Okay, so we know I is equal to EMF of the battery divided by R, 1 minus e to the minus r over L times t. And we know that di dt is equal to EMF over L equal, or e to the minus RT over L. So we're just using a couple different equations there. Okay, so from this we see I is equal to EMF of the battery divided by R, 1 minus e to the 0 is equal to 0. So there's no current when it first connects, which is exactly what we would expect. However, and this is where it continues to be interesting, di dt is equal to V over L is equal to 60 volts times 50 times 10 to the minus 3 henries is equal to 2.8 times 10 to the minus 4. And so we can see that the change in current right when it's first connected is non-zero, but it starts at 0. And so for this setup, what is the time constant? So tau is equal to L over R is equal to 50 times 10 to the minus 3 henries over 180 ohms is equal to 2.8 times 10 to the minus 4 seconds. All right. I am going to stop here, and I will see you for part 2.